Hey everyone, and welcome. Today, we're going to dive deep, and I mean really deep, into the vast, mysterious world of our oceans. We're going to explore the dynamic blue heart that literally powers our entire planet. So let's just start with one number that puts everything into perspective: 71%. A staggering 71% of our planet's surface is covered by water. There's a very good reason we call it the blue planet. But here's the really cool part. We give it different names: the Pacific, the Atlantic, the Indian. But in reality, we're just looking at different neighborhoods of one single, massive, continuous body of water that connects the entire globe. It's all one ocean. So, to get our heads around this huge topic, here's our game plan. We'll start with the sheer scale of our blue planet. Then we'll explore the incredible hidden landscape below the waves. After that, we'll get into what keeps the ocean moving, how that motion fuels life, and finally, we'll see how it all connects back to us. All right, let's kick things off by trying to grasp the unbelievable scale of the ocean and the science that helps us understand it. The field we're talking about is called oceanography, and really, it's the study of, well, everything about the ocean. It's all part of the Earth's hydrosphere. That's just a fancy word for all the water on our planet. And this system, it's a major driver of our climate, our weather, and pretty much life itself. Now, take a look at this breakdown of all that water. A whopping 97% of it is salt water, sitting right there in our oceans. That means only a tiny 3% of all the water on Earth is fresh water. And if we zoom in on that little 3% slice of fresh water, you can see most of it isn't even flowing in rivers or lakes. It's locked away, frozen in glaciers and ice caps. This just goes to show how completely dominant the ocean is in our planet's water system. So for our own sanity, we divide that one big global ocean into 5 major basins: the Pacific, the Atlantic, the Indian, the Southern, and the Arctic. And you'll want to remember the Pacific. It's the undisputed heavyweight champion, the largest and the deepest of them all. Okay, now that we have a sense of the scale from up here, let's dive beneath the waves. We're about to explore a hidden landscape that's every bit as complex and varied as anything you'd find on land. Let's walk through this, step by step. It all starts with the continental shelf, which is basically the submerged edge of a continent. It's shallow and full of resources. Then, you hit the continental slope, a steep drop-off into the deep. And down there, you find the abyssal plain, this incredibly vast, flat expanse. But it's not empty. It's cut by massive underwater mountain ranges called mid-ocean ridges and unbelievably deep canyons known as ocean trenches. And to give you an idea of just how deep we're talking, get this. The deepest of these, the Mariana Trench, is so deep that if you could place Mount Everest at the bottom, its peak would still be over a kilometer underwater. That is just mind-boggling. Now, the one thing the ocean never is still. So for our third section, let's look at all the incredible forces that are constantly churning and moving this colossal body of water. Ever wonder what makes the ocean salty? It's one of its most defining features, its salinity. On average, the ocean has a salt concentration of about 35 parts per thousand. All that means is that in every liter of seawater, you'll find about 35 grams of dissolved salts. But here's the thing, it's not the same everywhere. Salinity can change a lot depending on things like evaporation, which removes fresh water and leaves the salt behind, making it saltier, or rainfall and rivers pouring in, which do the opposite and dilute it. And in case you're curious, the main salt is good old sodium chloride. Yep, table salt. Temperature also creates these really distinct layers in the ocean. At the top, you've got the warm surface layer, heated by the sun. Go a little deeper and you hit the thermocline, a transition zone where the temperature just plummets. And at the bottom, you have the deep zone, where the water is uniformly freezing cold. Now, these differences in salt and temperature, they're a huge deal because they change the water's density. And that density difference is what drives the slow, powerful currents of the deep ocean. Of course, when we think of the ocean moving, most of us picture waves, and for the most part, they're caused by wind blowing across the water's surface, transferring its energy. The highest point is the crest. The lowest is the trough. Simple, elegant, and incredibly powerful. Then you've got the tides, that daily rise and fall of the sea level. It's all because of the gravitational pull of the moon and the sun. When the sun, moon, and earth all line up, their gravity works together to create extra strong spring tides. But when they're at right angles to each other, their poles kind of fight each other, resulting in much weaker neap tides. But maybe the most important movement of all comes from ocean currents. The best way to think of them is like massive flowing rivers inside the ocean itself. They act like a global conveyor belt, driven by wind, the Earth's rotation, and those temperature and salinity differences we just talked about. This is the planet's circulatory system. These currents basically come in two flavors. You have warm currents, like the famous Gulf Stream, that move warm water away from the equator toward the poles. And you have cold currents, like the Humboldt, which do the opposite. And this isn't just some random fact. This shapes our world. The Gulf Stream is the reason a city like London has a much milder winter than parts of Canada that are at the exact same latitude. It's a real-world climate control system. And all of this constant motion, it's not just a physical process. It is the very engine that drives and fuels life in the sea. Let's take a look at how. This right here is the perfect example of that connection. It's a process called upwelling. This happens when currents pull cold, deep water up to the surface. And that deep water is absolutely packed with nutrients from the ocean floor. When it hits the sunlight at the surface, it causes a massive explosion of life, creating some of the richest fishing grounds on the entire planet. Another critical ecosystem, coral reefs, also depends on very specific ocean conditions. They need warm water, shallow seas, and plenty of sunlight to thrive. You see a few different types, like fringing reefs right off the coast or huge barrier reefs. And what's really amazing is that Australia's Great Barrier Reef is the largest single structure made by living organisms on Earth. It's so big you can see it from space. So, for our final section, let's bring all of this together. Let's talk about why understanding our oceans is so incredibly important for every single one of us, no matter where we live. So, what's the big takeaway here? The ocean isn't just a big, wet place on the map. It's a complex, dynamic system that regulates our global climate, provides us with food and energy, and is home to an incredible diversity of life. From the currents that warm our cities to the unseen trenches in the deep, every single part is connected. And what happens in one corner of this global ocean truly affects us all. It's a world we've really only just begun to explore, which leaves you wondering, what other secrets are still waiting for us in the deep?